So what is a capacitor? Well, it's not by chance that the symbol for a capacitor consists of two plates, because that's effectively how a capacitor is actually made. It's made of two different metal plates which are separated by an insulator which they call a dielectric. And a dielectric is just an insulator in between those two. So effectively there is no circuit between one plate and another. So the way to make a capacitor better is to bring these plates closer together, so potentially by changing the dielectric, which dielectrics can be air, they can be polystyrene, they can be paper, they can be mica, or the best ones they tend to do are electrolytic, which is basically they oxidise one side or both sides of these plates to insulate them from each other. What does that effectively do? It means the plates effectively can be closer together. So to increase the efficiency or the potential energy stored, which is effectively what a capacitor does, is the way you tend to do that is you make the plates go closer together, or the other way to do it, and obviously it's a combination of the two, is these plates obviously make them bigger. Okay, so the bigger these plates happen to be, then the better the charge will be that effectively can be stored on a capacitor. So that's effectively what a capacitor does. A capacitor stores energy. It's not a battery, because batteries can hold much more capacity. So capacitors, however, are very quick to charge, but they're also rapid to discharge. Okay, so they can hold relatively smallish amounts of energy within it. So that's basically what a capacitor is two plates separated by a dielectric, which effectively is an insulator. So how does it basically work? Well, if we just take a typical symbol here of a capacitor and we connect it to a DC supply there. Now obviously this is the positive, that's the negative, and when you connect this up, current will flow, because although there's no circuit as such, well, there is no circuit, there's not as such about it, there's no circuit because there is an insulator in between this, which remember is a dielectric. What happens is this is positive, this is negative, and as we know then the flow of current is electrons, and electrons being negatively charged are attracted to the positive charge. So electrons disappear off of this plate and get added to this plate. Okay, so if you take electrons away, what you end up with is this becomes a positive charge and that one becomes a negative charge. And so current will flow, but it won't flow forever, not with this type of supply, because remember this type of supply is a DC supply. So how can we basically show that? Well, the best way to do it is with a graph. So this is time going in this direction, and what we'll do is we'll show, first of all, we'll show current. Okay, we'll do current first of all, and we'll do current in red to show what happens as the current starts to flow. Now, when the moment you turn this on or connect it up, maximum current flows because this is completely neutral. There is no overall charge on the capacitor. So what you get is current will start to flow, and electrons are disappearing off of there and appearing on this side. So they have a maximum current flow, but obviously there's only a finite number of electrons. There's still a lot of electrons, don't get me wrong, but what happens is this occurs. So it starts to drop quite rapidly, and it will keep getting closer and closer to this bottom line being zero down here, but it will never ever reach zero. Even if it went for infinite amount of time, it will just get closer and closer. So smaller and smaller amounts of electrons keep disappearing away. So that's basically what happens is the current is large to begin with and then starts to drop away. Now this has the added different effect of, if we put a voltmeter and we could measure the voltage across that capacitor there, what happens is the voltage goes the other way. So it starts off, there's no overall charge on the capacitor plates, and it does this. And the overall charge starts to go up, and again what it will never do is it will never reach the maximum voltage. So if this was, let's say, 50 volts, this will never ever get to a maximum of 50 volts across this capacitor. So it keeps going up and up and up, and effectively it will follow that line and they'll just keep going, being closer and closer, but never actually reach. So that's what happens to the volts, and that's what happens to a capacitor when connected to, remember, this is a DC supply. Now, how quick does this take this to happen? Well, it happens quite rapidly. There's something called, and depending what course you're on, there's something called a time constant for it, and that is a measurement of C times R. Now, that we've not introduced so far is this holds charge, and the charge of a capacitor is measured in farads. Okay, so Michael Faraday, that's who it's named after. So it's measured in farads, and typically the value of farads is very small. The symbol for farads is F, is what we tend to use, but it's normally quite a small figure, so it's actually typically in the micro farads region, which you will see is times 10 to the minus 6, or which is equivalent to 0.000, and it's down here. So this is the micro region. So typically capacitors are down in this value. So farads is typically down here. It's a very small number. There are such capacitors that are called supercapacitors, and they would definitely be, they are large. Okay, so they tend to be used where you want to hold an enormous amount of charge in comparison. So there's your typical capacitor, and this here is called the time constant, which is what I was referring to, and it's the capacitance times the resistance, and this gives you this thing here, which is the time constant, which is the amount of time it takes to charge to 63% of whatever the value of that capacitor is, and C is the capacitance. So we give the letter for it is C, okay, which is measured in farads, times R, which is the resistance, and that would typically be, so if we added it to this circuit here, it would be a resistor in series with that circuit, and that will limit the current flow. So if we put some figures in, so if we made that 1 kilo ohm, and let's give this a figure of 15 microfarads, it would basically become 15 times 10 to the minus 6 times 1000. And that would be seconds. And basically what that means is it would take 0.015 of a second to charge that capacitor up here, effectively. So I changed the colour just to show that approximately what's 63% roughly there. So that would be one time constant to get to that point. And what they basically say, what the manufacturers say, and what the theory tells us is effectively, because this never reaches maximum and therefore this never reaches minimum, a capacitor is fully charged after 5 times the time constant. So 1, 2, 3, 4, 5, and effectively it will be fully charged after that. So 5 times 0.015, so 0.075 of a second, that capacitor would be fully charged. That's fairly quick. Obviously, if you compare that to a battery, it would take much longer to become charged. However, a battery would hold much more charge overall, and energy is what it would hold. So these are very quick, rapid charging, which can be varied by putting different resistors in for a given supply. and that will become fully charged, but the thing is then it can instantly give you that energy very rapidly. Okay, so what we've done now is let's assume that this was charging, got to 5 times its charging, charged the capacitor, and then the battery was removed in the process of charging. So what happens to that there? Well, effectively, like a battery, the capacitor will hold on to its charge. So these stay positive, these stay negative. Now these capacitors in certain appliances, that can be quite dangerous because they do hold a charge. And if you was to stick your fingers across them, all of that energy would discharge into you if you happen to put your fingers across them. So we have in our regulations that all capacitors in the electrical system must have a discharge resistor built into them. So if you ever see a capacitor in a fluorescent light or a load of some description or whatever it happens to be, you probably won't see the resistor, but the manufacturers have put a resistor internally within the construction, literally across the supply. So effectively when the supply disconnects, it will self-discharge itself back through the resistor, which means when you isolate the supply to something, if you think of a building might have many capacitors in the supply, if you didn't have those discharge resistors, when you turned the supply off and you thought you were safe isolating, all of those capacitors would discharge back into you if you happened to put your fingers across the terminals that you thought you'd isolated. So discharge resistors must be installed in capacitors that are used on our electrical supplies themselves. But the manufacturers do all this for you, you don't need to worry. So we don't have a discharge resistor on this, we've just got capacitors charged, and what that will do is it will hold on to its charge, and depending how good the dielectric is, in theory it could hold on to it for an infinite amount of time if it was a really good dielectric. In other words, the electrons can't flow back anywhere, so you've effectively still got that one positively charged, that one negatively charged. So what would happen then if we connected, let's say, a lamp across that? Okay, what would basically happen is it would discharge into that lamp, and that lamp would then glow, would become bright for a very brief period until all the electrons have disappeared and they've effectively balanced out to nothing again. And that would happen quite quickly. The way you could control that obviously is to have a resistor, and you can limit the amount of current to discharge it over a longer period if that's what you wish to do. So what would basically happen now, if we remove the lamp and we just put a dead short in it, the current that would flow would suddenly do the opposite way around. The current would flow, would be a lot, and then disappear quite rapidly, and the voltage would drop enormously. So these would then start flowing, but only for a short period, and that's what would happen on DC. So effectively, if you did this on a capacitor, it would go bang. So we can work out the charge on that, because it can be V times C, where V is the volts, C is the capacitance, and then you could work out how much charge in coulombs you have on that capacitor. What you could then do is work out how much discharge you would get, and that would be Q divided by the time taken. So if we just applied that based on this 230 volts, let's assume it got to times 15 microfarads, so that's 0.000015, and that comes to 3.45 millicoulombs. We can then apply this down here because we can work out how quick. So let's say with 3.45 times 10 to the minus 3, and let's assume it was discharged in 100 microseconds. So 100 microseconds would be 100 times 10 to the minus 6. That would give you 34.5 amps. So you can see why it would make quite a large bang. So for that particular capacitor there to discharge in that amount of time with only 3.45 millicoulombs, you end up with 34.5 amps would flow. So it would only be there for an instant, but it would go bang, and if you stuck your fingers across it, you'd know about it. So what happens now, it's connected onto an AC supply. Well, now it's connected on an AC supply. Obviously, as we know, the sine wave is constantly going up and down. So what effectively happens is, here is our voltage. And now what happens is the current will appear to flow. So if we put an ammeter into this here, when we put it on DC, what would happen is this would go maximum and then start dropping down quite rapidly as it becomes charged. However, on AC, what's happened now is when you put the supply on, you've got the positive half of the cycle, current will start to flow and charge these capacitors upwards as it does, the electrons migrating until it gets to this point here. And then as this starts to drop, what happens is the current, there's not enough force from the voltage to hold those electrons there, so the electrons start actually migrating back again until you get to this point here where now you've got it going negative. So what you've done is you've actually tried to make, let's go with this side is positive initially, so these become positively charged and this becomes negatively charged. On the next half cycle, what happens is it's trying to reverse that and tries to make this side the positive charge and then that side the negative charge. So what's actually happened is the current, unlike in DC where it goes one direction only, in AC what you've got this going on all the time. So this actually would read, if we put it connected up, because it reads RMS, would read a constant figure. Now the bizarre thing is, what happens with this now is the moment you turn it on, the current does this, you end up with maximum current initially dropping to 0, and you get this. You get a sine wave, still a sine wave for the current, however it is now out of phase with the voltage. So it's bizarre because what you end up with is 0 volts but maximum current, and when you get maximum voltage you get 0 current, and same here. So 0 voltage, maximum, 0. So it's out of phase by 90 degrees. Now these are quite difficult to draw, so it's easier to draw phasor diagrams. So what we'll do is we'll make the voltage the reference, and we always go right to left with a phasor diagram, and it goes round in a direction by 2 pi f or omega, which is 2 pi f. Okay, that's the spinning velocity because that's an angular velocity is what it is. And the current is 90 degrees out of phase, and it's leading because this is going anti-clockwise. That's a very badly drawn line, but you get the idea. That would be the current, and it's out of phase by 90 degrees. So this is a representation of that. This is much easier. So it might make it look difficult, but it's much easier to draw because it's an angular velocity. Now, because there's current flowing in this particular circuit, and it isn't an infinite amount of current, it's a finite figure that actually flows when we connect this up to a circuit, it must mean there's something limiting the amount of current flowing, and anything that limits current flow is measured in ohms. Capacitive reactants, and capacitive reactants is a formula which is XC, and it is 1 over 2 times pi times the frequency times C. Now 2 times pi is to do with this, and F is the frequency to do with that there, so it's angular velocity, and that's what that bit is, hence they sometimes referred to as omega, times C, which is the capacitance of that capacitor, and then you divide it all into 1. So on a previous example, if we work one out, let's give it 100 microfarads. Okay, so that becomes 1 over 2 times pi. I'm not going to write pi in times 50 because that's what that is, times. Let's put those as times so you know. So 100 times 10 to the minus 6, remember. And that comes to 31.83 of an ohm. And now if we apply the voltage, so that would be the opposition to current flow for this particular circuit here, based on the frequency. And now we could work out what the current would be if we put a voltage in. So if we put a voltage in, let's give a V equals 100. We can now work out what the current would be for this current up here. I is basically back to Ohm's law again. It would be V divided by an ohmic value, but it's not. Obviously R, we divide it by XC. So 100 divided by 31.83, 3.14 amps. So that's how much current would flow round in this circuit here, and because it's basically charging and discharging, but the bizarre effect is it puts the voltage and current out of phase, and it's a leading current. And if we cast your mind back, or if we have a look at, we have this thing called civil, and this is now we're now looking at this set here, and in a capacitive circuit I leads V, and that's exactly what it's doing because it's going around in an anti-clockwise, and it's because it's a pure capacitor, and a pure capacitor has 0 resistance. It's out by 90 degrees. Okay, there's a circuit then that has a 150 microfarad capacitor on a 230 volt supply, and basically what we're asking for is what is the current that would flow if it was 50 or 100 hertz. Well, first thing we need to do is work out XC. So XC is 1 over 2 pi FC. So we can put that in, we know that bit, that's straight away, and XC, so this will be at 50 hertz. Okay, so we'll put that in, so that's 2 times pi times 50 times 150 times 10 to the minus 6, and we can calculate what that would be, and that comes to 21.2 ohms. We can do the same now at 100 hertz. So same formula, so it's going to be 1 over 2 times pi times, not 50, again, times 100 times 150 times 10 to the minus 6. So you can see what happens as the frequency goes up, the ohmic value goes down. So what we can see now is that the current will change, and as you can see, look, if the frequency doubles, then the current will also go up with it, because it's charging and discharging more rapidly. So how do we work out the power in a capacitor? Well, first things first, let's work out the current. So to work out the current, that formula for that is V over XC, which we know what V is, that's 118 However, at the moment we don't know what XC is, so we need to work out XC, and XC equals 1 over 2 pi FC. So if we put those numbers in, 2 times pi times 50 hertz times 15.78 times 10 to the minus 6. If we calculate that, 201.7 ohms. So we can now put this figure down in over here, 201.7, and we can work that out. So if we work that out, that is 0.585 of an amp. So you might be inclined to go, well, I'll do V times I. So if you've got your voltage, that's 118 times by 0.585, and if we work that out, that gives you 69. Now what you might want to do is put watts in. Okay, that's what you might want to do. You'd be inclined to go for all of that. How I would say is, this isn't power for this circuit, and that will not be the power, and we can show you that. So I've got one set up, and if you look now, when you connect this up to the circuit, and we get 118 volts connected to a capacitor on a 50 hertz supply, 118 volts to this capacitor, and we click on the wattage, what you can see is the wattage is practically zero. Now the reason it's practically zero, because it comes back to our earlier graph, which is that there is our voltage, and that is our current. And basically, if you work this out now, the power, because it's 90 degrees out of phase, the power does this. To pop the power out, not certainly best to run like this, but effectively that's what happens to the power. So you end up with a positive and negative of power all the time. Overall then the power is nothing, because all the energy goes in, goes back out again, and nothing gets used. And this is as close to pure as you can get with a capacitor. So actually the overall power is this. Now the formula for that is, if we want to use V times I, is V times I times the cosine of the angle. And if we apply that, that's 118 times 0.585 times the cosine of the angle. Now the cosine of the angle is how far out of phase these happen to be. Okay, so it's the cosine of 90, and if you put the cosine of 90 in a calculator, what you get, if you can see that, is 0. So the cosine of 90 degrees, that's how far out of phase, is 0. And if we put that into our formula, 118 times 0.585, and anything times by 0 is 0 watts, which actually ties up with the meter when connected to this circuit. So this is the correct one for power. This one is not power. What you've actually calculated here is something called the VA, which is something called the apparent power, and therefore the unit is not watts, it is literally VA. Now the things where you see VA, generators, transformers are measured in VA, because they don't know what watts you're going to use, they don't know what the power factor of the equipment you're going to use. So VA is what the actual apparent power of that circuit happens to be. The true power, which is what this is actually 0.